Hello everyone, here we'll be discussing 2.2, which is a section on limits of a function. So here I give this definition. This is what is called an intuitive definition. It's not a precise definition of limit, which we'll actually discuss in a later chapter. But anyways, right now, let's say, suppose f of x is defined when x is close to a. Now, as far as what that means is that f of x will be defined on an open interval containing a. But that's a little technical, but you can think about that more if you like. Then we use this language here. And of course, this in words is the limit as x approaches a of f of x equals L. So this arrow notation under the limit means approaches. So as x approaches a, f of x will get closer to L. So in words, if values of f of x approach L as values of x approach a. So values of f of x will get closer and closer to L as our x values will get closer and closer to a, which I know sounds a little bizarre, but really what we're trying to do is plug a into f. But it's not necessarily the case that you can always do that. And I give a few examples here below. So here for the first example, you can actually plug 2 in. And notice if you plug in values that are close to 2, then you'll get values that are close to whatever this value actually is at 2. And of course, if you just plug it in, you'll get 2 squared is 4, minus 2 is 2, and then plus 2 is 4. So this limit is actually equal to 4 as it turns out, but that's because this function, we call this f of x in this case, this function is actually defined at this a value 2. Opposed to this example here, we're approaching x equals 1, but when you plug in 1, you get 0 over 0, which is undefined actually. So here, we're plugging in values that are closer and closer to 2, but you can actually plug in 2 itself. Here we can't though. So now again, as it turns out, if you plug in values that are close to 2, the resulting f of x values will get closer and closer to 4. So if you plug in, let's say 1.999 or 2.001, two examples of numbers that are close to 2, you'll get results that are close to 4. So try that on your own, I encourage that. Here, what exactly do we get? Well, I'm going to actually unveil something to us. And it's basically a method we'll be seeing a lot in this section. And we'll see other methods as well. But what I'm going to do is I'm going to try to factor as much as I can and then cancel any factorization. And that's of course only because when you plug in the limit directly, you actually get a 0 over 0 form. So notice if you plug in 1, you get 0 on top and 0 on the bottom. So this idea of plugging in is referred to very often as direct substitution property, or DSP for short. So we very often try to apply DSP. If you do it and you get a number, then that's your answer. But if you do it and you get 0 over 0, this is what is known as an indeterminate form. And if you get an indeterminate form like 0 over 0, it means you can go back, try to manipulate the expression somehow so that we do not have an indeterminate form after plugging in the value, which is kind of bizarre, but let's see if we can do that. Here we can definitely do that. If you factor the bottom in this case, it factors as x minus 1 times x plus 1 because of difference of squares from algebra. And now notice that you can actually cancel the expression x minus 1 on top and bottom. And really this is just now the limit as x goes to 1 of 1 over x plus 1. And now if we try DSP here, we get 1 over 1 plus 1, which is of course just 1 over 2. So here the limit is 1 over 2. And if you try to plug in numbers that are close to 1 into the original expression, you'll get values that are close to 0.5, which is just 1/2. So now we're going to take a look at a few different types of examples. And then from there, I'll try my best to explain different techniques, such as this, to find limits of any given expression. All right, so these are two kind of specific examples. This one is actually basically the last example we saw, where we have this piecewise function, g of x, where g of x is defined to be that expression we saw, x minus 1 over x squared minus 1, when x is not equal to 1, and 2 otherwise when x is equal to 1. Now what this kind of does is actually gives a function that is defined everywhere. The only places that this was undefined Actually, I kind of lied. This is undefined when x is -1 as well. Notice when you plug in -1 squared minus 1, it still gives you 0 in the bottom. So g of x isn't defined everywhere actually, but it is defined when x is 1. So g of 1 is actually equal to 1. So if you apply DSP into, not 1, I'm sorry, it's 2. When x is 1, g is 2. So if you apply DSP to this limit, technically, as x approaches 1 of g of x, technically by DSP you get 2. Now, the idea behind direct substitution doesn't actually apply to weird functions like this where you have a piecewise defined parts going on. And the reason being is because it is not one continuous function, it actually has a break and a jumping point somewhere, which we'll discuss later on when we discuss continuity. But what I want to do here is I'm going to graph this to give you a visualization of what's going on. And to be quite honest, once you graph a function, it'll give you a really, really good idea as far as what the limit is doing. So we can graph x minus 1 over x squared minus 1. And if you do that, you'll actually get something that looks kind of like this. It has a horizontal asymptote at x equals -1. And, sorry, not horizontal, but vertical. And then over here, it kind of looks like this. But I'm going to worry about this side. Now, when x is equal to 1, we have a hole in this function. And the reason why is because, notice what we did earlier, we actually factored out x minus 1 from the bottom and canceled. So really what you get there is a so-called removable discontinuity. But again, that technical discussion is for a later section. But for g of x specifically, we get 2 for x equals 1. Which I know sounds kind of weird, but that's kind of what can happen when you have these so-called piecewise defined functions. So now notice this is still a function. It doesn't actually fail the vertical line test here because it only passes through this vertical line once at this point. Since this is an open circle, it actually doesn't touch that point, it touches this point only at that vertical line. So this is what the graph looks like. Now notice, as x approaches 1 from either side, the y values will approach the y value of this hole, which so happens to be 1/2. So even though we are actually defined at 1 with this piecewise defined function g of x, it doesn't actually matter. Because approaching x equals 1 from either side of 1, the y value will still approach 1/2. So from our definition of limits, this should be 1/2. Kind of from a graphing perspective. So it's nice to have the graph. Once you have the graph, you can better visualize what the limit is actually doing and how things are behaving there. Here, I've kind of done things a little differently. So we call this expression f of t. We want to find the limit as t goes to 0 of f of t. And notice this is not a piecewise defined function, so DSP would work. But you get a denominator of 0 situation, so we actually can't apply DSP. So instead what I've done here is I've created a table where I plug in plus or minus these values. And we end up getting the same answer no matter if it's plus or minus. So if the plus or minus is bugging you out, I wouldn't worry about it too much. Just plug in numbers that are close to 0 on either side of 0. And we end up getting these. And notice these numbers are getting closer and closer and closer to 0.1666. And if you had good recognition of decimal approximations of fractions, you'll know that this is approaching 1/6. So our guess is that this approaches 1/6. Now this is a guess based on the table. So you can always do this, and this is kind of what I led you to believe when we did those previous examples, as far as, again, just kind of comparing what the values are approaching. And this actually is the answer, believe it or not. But the whole point of this example is you kind of have to be careful. Because if you go too far off and plug in, let's say, 0.000001, this should actually be really, really, really close to 1/6. So it actually should be this. But if you do this in your calculator, of course, if you have a really, really advanced calculator, like if you're using a computer, for instance, it'll probably give you 1/6 or 0.16666. But according to my calculator, and I have a TI 83 Plus, it actually gave me 0. And the reason being is because the first thing the calculator is actually approximating is this radical part. And when t is really, really close to 0, this radical part is close to 3, and 3 minus 3 is 0. So it sees it as 0 over a number. And yeah, calculators actually approximate, believe it or not. Specifically when you have something that's way, way far out there. So it's a little scary when you think about it because, again, you have to you have to be close to what you're approaching, but if you're too close, maybe your calculator can fail you. So just kind of bear that in mind. So now what we're going to do is we're going to discuss this idea of what I was saying here as far as approaching from both sides. I even said it here as well. There are certain cases where you approach from one side, you get a value. Approaching from another side, you get a different value. In fact, here, if you actually completed the graph here, at -1, there is a vertical asymptote, like I mentioned earlier, which is actually not of particular interest to us for this problem. But then the other side of the graph actually looks like this. So if you want to find the limit as x goes to -1, on this side it seems to go to positive infinity, but on this side it goes to negative infinity. And in that particular case, as it turns out, the limit doesn't exist. And that is possible, and we'll dig a little deeper into that discussion right now. All right, so now we break up the idea of a limit into two sides, plugging in numbers that are less than what we're approaching and plugging in numbers that are greater than what we're approaching. In other words, plugging in numbers to the left of the number or to the right of the number. And these are known as the so-called one-sided limits. So this little negative and positive that kind of look like exponents really tell you what side we're approaching A from. So this is the limit from, let me use red here, just so we have some contrast in color. So this is the limit from the left, whereas the other one where we have a positive exponent symbol, this is from the right. And again, really all this means is that we're approaching A from the right and we're approaching A from the left, respectively here. So we're only plugging in numbers that are smaller than A, we're only plugging in numbers that are less than A. So why do we use from the right and from the left? Well, just kind of think of how the number line works. If you have A and you're approaching A from the right, then you're plugging in numbers that are bigger than A. Similarly, here, if you're plugging in numbers to the left of A, you're plugging in numbers that are smaller than A. And really where that notation kind of comes from is that negative numbers tend to be on the left, and then positive numbers, of course, are on the right. So that's one way of kind of thinking about that. The plus we think of as the right side, and negative we think of as the left side of the number line. Good. So now I have this pretty important statement here, honestly, and it actually tells us when limits don't exist. So it says the limit of f of x equals L as x approaches A. And notice there's no plus or minus symbol here. So this is the usual limit. And now you can kind of think of it, if you like, as a two-sided limit. That's really what we've been looking at. We've been plugging in things to the left and right of a number, and so bigger and smaller than a number. And we're using that to determine the limit of the function itself. So we say that the two-sided limit exists and is equal to L if and only if the left and right-hand limits exist as well and are equal to the same value. So only if your left and right limits both equal L, then your actual two-sided limit without the funny minus or plus symbol is actually also equal to L. So here I give a visualization problem where I give you the graph. And consider this the graph of, let's call it g of x. And let's find a few things. Let's find the limit as x goes to 1 of g of x, and let's find the limit as x goes to 4 of g of x, just based on the graph alone. And we can definitely do this. Okay, let's see what we get. So for 1 is bad news, because notice, if you look at the vertical line that has x equals 1, approaching from the right, we get -1. As x approaches numbers from the right, the y value g of x approaches -1. But from the left, we actually approach +2. And since 2 is not equal to -1, then this limit actually does not exist. So I should have completed this here. Otherwise, the limit of f of x does not exist. So D and E stands for does not exist. So again, the only time limits do not exist is when the one-sided limits do not agree with each other. So the only reason why that's true for 1 is because, so let me write here, because the limit from the left is equal to what? The limit from the left would be equal to 2, and that's not equal to -1, which is the limit from the right. So limit 1 from the right of g of x. Perfect. Okay, good. So since the limit from the left and right are not equal, then the limit doesn't exist. Great. But here, notice if we approach 4 from the right or left, we actually get the same y value because we're on the curve here, and that's also 2. So, well, it looks like it's 2 anyways. So here I'm going to say that's 2, so the limit actually exists because from the right or left you get 2. So if I wanted to write in red, limit from the left equals 2, limit from the right equals 2, so that means that this limit exists and is equal to 2. So for part 1, D and E, or for part 2, does not exist. Perfect. So now we're going to talk a little bit about something that still involves these one-sided limits, but now we're going to deal with infinity. Alright, so the last one we need to discuss, of course, are infinite limits, where we have a scenario where the limit as x goes to a of a function f of x is equal to infinity, and in fact you can actually have approaching infinity or negative infinity. Now, these are the two most basic classic examples, and this will actually unveil to us what's really happening and a better way of actually finding out what scenario we have. And I'm going to tell you right away that when you have a scenario where you actually have a limit that is positive or negative infinity, then this is actually describing a vertical asymptote, which hopefully we've seen before when it comes to algebra. And I described the vertical asymptote actually in an earlier example. That's where we have this kind of imaginary line that's not there, that's a vertical line that the graph approaches but doesn't cross or touch. Okay, so here, if you actually graph 1 over x, the image will look like this. So it has a horizontal and vertical asymptote. If you graph 1 over x squared, the graph actually looks like this. So by the way, what this limit being equal to infinity or a negative infinity really means is that we can pick values of x to be closer and closer and closer to a, so that this number, the resulting f of that number that you're plugging in, will just get larger and larger and larger and out of control large. So it's approaching infinity is what we say. Or if it's approaching a negative large number, then we would say that would approach a negative infinity. So in this case, we actually kind of see that, but from a more graphing perspective. So notice here, the limit from the right actually approaches positive infinity. So let me write that. Limit as x goes to 0 from the right of 1 over x is approaching positive infinity. Good. Because as x goes closer and closer to 0 from the right side of the x values, we see that the y values of those will just get closer and closer and closer to the y-axis. So it's actually approaching, the y values are getting larger and larger. And you can check that out by plugging numbers in. Notice plugging in a number bigger than 0, so to the right of 0, that's close to 0, so like 0.00001, 1 over that will just be the reciprocal of a really, really, really close to 0 number, which will give you a very larger number. In fact, just for instance, 1 over 0.001 should give you 1,000 actually, because 0.001 is 1,000. So the reciprocal of that is 1,000. But again, I'll leave that to you to figure that out on your own using calculators and kind of experimenting. And that's honestly the best way of figuring these things out, is just experimenting with the calculator and seeing how numbers behave really. And now notice approaching from the left, that the opposite happens, we approach negative infinity. So let me write here that the limit as x goes to 0 from the left now of 1 over x is actually negative infinity. And what does that tell us? It tells us actually that these two limits do not agree with each other. They do not approach to the same infinity. So in fact, this limit doesn't exist. In fact, let me write that here. This limit does not exist. If you want to write equals d and e, I guess you can do that, but it sounds a little silly to me because it's not equal to d and e, it just does not exist. So I don't write the equality there. It just doesn't exist. From the right and from the left do, but they don't agree, so the limit doesn't exist. Good. All right, what about 1 over x squared? Well, you can see from the graph here that they actually approach positive infinity from the right or left. They both approach positive infinity, so this will actually equal positive infinity. And if you don't want to write the plus, just write infinity on its own, that's fine too. And I didn't actually write the limit from the right and left, but again, if you try that on your own, you'll see that they'll both approach positive infinity, and that's of course because when you square a negative number, it's positive anyways. Opposed to here, it would have been negative. So in fact, something I kind of want to say is that recall that when we looked at indeterminate 0 over 0 when you try DSP, here we get an undefined number when you try DSP. We get 1 over 0, 1 over 0. So really what the form we're looking for here is a number over 0. So if you try DSP and you get a number over 0, this tells you that you have this vertical asymptote scenario and you have to plug in numbers to the left and to the right of whatever you're approaching. If you approach to the left and right and you get different signs, then that means it does not exist. If you get the same sign and they're both positive, then chances are a number over 0 is telling you that there is a vertical asymptote there and you're approaching positive infinity. Otherwise, you'd be approaching negative infinity if the signs are both negative when you plug in numbers from the left and right. So again, these are the most classic examples when it comes to these vertical asymptote infinite limit scenarios, but I want to show you 2 more that are infamous in their own right, but not classic like this. And let's see those, and that'll be it for the video. Okay, so those 2 extravagant limits I was talking about, of course, are the limit of tangent and limit of ln of x, where we have these kind of vertical asymptote scenarios. So just to remind you, I'm going to graph each of these. So the graph of tangent looks kind of funny. It basically looks kind of like this cubic looking thing, only we have vertical asymptotes at pi over 2 and negative pi over 2. And this actually repeats. This is kind of the, reminds you of a period of a trigonometric function. So we have this repeating indefinitely to the left and right for every interval length of pi. So this is going to be 3 pi over 2, and that of course will be negative 3 pi over 2 for this not horizontal, but for this vertical asymptote. Okay, perfect. So now we can kind of tell from the graph alone that, well, from the left, it approaches positive infinity, or from the right, it approaches negative infinity. So that tells us that this limit actually doesn't exist. But if we had, let's say, a plus sign, so let me kind of change that, then from the right, it actually approaches negative infinity. And then let me just write from the left, it approaches positive infinity then. Now, a really nice way to discuss this beyond the graph, or I guess before you would consider the graph, is the fact that tangent is equal to sine over cosine. So you can kind of see what happens to the denominator here at pi over 2. Cosine of pi over 2 is 0, but if you plug in numbers less than pi over 2, kind of think of being in the first quadrant, cosine would be positive. Sine is also positive in the first quadrant, so less than pi over 2, we're positive, but as you approach pi over 2, it's 1 over 0. A number over 0 reminds you of a vertical asymptote, but since we're approaching from the right, from the left, being less than pi over 2, we get positive numbers. However, if you're bigger than pi over 2, let's say in the second quadrant, sine is positive still, but cosine is negative now, so that will result in a negative number that's close to pi over 2 on the right, so that means bigger numbers bigger than pi over 2, and you get negative as a result, so it'll approach negative infinity. So that's a way of thinking about it without actually graphing. Good. Now here I have to put a plus. The reason being is because ln of x, if you look at the graph here, has a graph like this. So this is y equals ln of x. Now, why it looks like this is because ln of x, recall, is the inverse function of e to the x. So if e to the x equals, maybe this is a better way of seeing it. if x is equal to e to the y, then this is true if and only if y is equal to ln of x. So it's the inverse of e to the x. So just as an example, since anything to the 0 is 1, e to the 0 is also 1, and that actually implies, and vice versa, that, well, let's see. So if we swap these, we get 0 is equal to ln of 1. So if you plug in 1 into ln, you get 0 as a result. But now the question is, well, what number will you plug into e that will result in 0? That's what ln of 0 is trying to tell us. Now, if you graph e to the x, so here I kind of use all of our space, but I can use some space here, I guess. So this, for instance, is a graph of y equals e to the x. And notice there's a horizontal asymptote at the x-axis. So what that says is that as x goes to negative infinity, e to the x approaches 0. So e to the x can never be equal to 0, but it approaches 0 as x goes to negative infinity. Which makes sense here, because if you look at this graph of ln of x, as x gets closer and closer and closer to 0, the y values get closer and closer to negative infinity. Okay. Also notice from the right, this is from the right, but notice from the left, actually there's nothing happening because the domain of ln of x is only 0 to infinity, open 0 to infinity. And that's because e to the x, since e is a positive number, it's about 2.71828, then it actually doesn't achieve negative numbers at all. Taking a positive number to any power will only result in positive numbers, never negative numbers. So for that reason, we have to approach it from the right, because approaching it from the left, the limit clearly won't exist because you can't even plug in numbers less than 0. So for that reason, it's equal to negative infinity. So it's also true that as x goes to negative infinity, e to the x will get closer to 0. And that's just describing a horizontal asymptote, which is kind of the reverse limit definition way of describing horizontal asymptote as to describing vertical asymptote, as we saw previously. But again, that's a discussion for a later time. Perfect. So it's a good place to stop here, and I'll see you in the next videos for 2.3 and beyond. Really hope you enjoyed this one, like always. Thanks for watching, and I'll see you then.